Here in this video onwards, we will see the procedure of applying variational method. So I have already told you this method will be generally used when you have a knowledge of the Hamiltonian of the system, and the content or the most fundamental procedure of the method is involving the evaluation of the energy eigenvalue using the expression for the expectation value of Hamiltonian. But the evaluation of the expectation value of Hamiltonian require a knowledge about the wave function representing the system. How we will resolve the problem of identifying the wave function representing the system? Because once you have an idea about the wave function or a possible wave function, definitely you can evaluate, say, E as equal to scalar product psi H psi divided by scalar product psi by psi, provided psi is not normalized. If it is normalized, this denominator will be equal to 1. Once you have evaluated this, of course you can apply the variational principle, say delta E equal to 0, and that will permit you to evaluate some constants. Then what are these constants that are also not involved, or say that are also not even discussed? So we will now see this. So to go with the variational method, we require a wave function. Here in variational procedure, we call this wave function as trial wave function. Another name that it is a trial one. It is a trial that we are making with the help of a speculated or guessed wave function. So to begin with the variational procedure, we actually require a wave function. We call it a trial wave function. And how we will then identify such a wave function, and once that wave function is being identified, then what will be the procedure of applying the variational principle? It is that exactly we will have to discuss in this section. So to apply the variational method, we will follow a systematic procedure, and I have written here the step-by-step procedures that are to be followed to apply the variational method. The first step, we will have to make an educated guess. I will call it an educated guess. It's not a mere guess. We will be invoking so many parameters, ideas and concepts about the problem that is to be solved while making this guess of the wave function, trial wave function. That is why this guess is referred to as a genuine guess or an educated guess. And this guess is based on the physical intuitions of the problem or the system under our quantum mechanical study. And this guess is taking into account these several different fundamental qualities that are to be possessed by the wave function or a well-behaved wave function. That include the physical properties of the ground state. Basically, once we are applying this with a greater validity to the ground state. Symmetry of the wave function. What will be the nature of this wave function? Whether it can possibly be a sine wave. Taking into consideration symmetry of the wave function, number of nodes that are present for the wave function. Say for example, suppose we are solving the particle in a box problem using variational method. In the ground state, we know that there are nodes at both extremities, whereas in the first excited state, there must be nodes at the center of the box as well as at the two extremities. So that is a quality possessed by wave function. And the smoothness of the wave function, whether there are any possible peaks or kinks present in the wave function. Behavior of the wave function at infinity. This is also a general property of all wave functions. So taking into account all these systematic, say, parameters, we will make an educated guess about the wave function that will be most suitably representing the system under our study. So there is no question of any knowledge about the wave function other than this. We have no idea about the exact mathematical behavior of the wave function. We will check the qualities of this wave function under the behavior towards these fundamental properties possessed by the wave functions, and on the basis of that we make an educated guess about the wave function representing the system, say psi. And keep in mind, while making such a guess, there might be properties we are not sure about whether this kind of property will be affecting the wave function or not. This kind of parameters are referred to as adjustable parameters. Corresponding to each and every adjustable parameter, we introduce as constants, say alpha 1 corresponding to one adjustable parameter, alpha 2 corresponding to possible another adjustable parameters. And this in fact form the vitality of the approximation procedure. If you are able to incorporate as many good number of most suitable adjustable parameters, you will be getting a most suitable wave function representing the system. That may be different from the true wave function in terms of one or two parameters or more than one or two parameters. This matching between the absolute true wave function and your trial wave function will also be deciding the accuracy of the approximation procedure that we are using. So this is the first step, make an educated guess on the trial wave function. In this usage educated guess, all these parameters are included. We are analyzing the physical properties of the ground state, symmetry of the wave function, number of nodes present in the wave function, smoothness and behavior of the wave function at infinity. And corresponding to those parameters not sure, we incorporate adjustable parameters, say alpha I. So mathematically psi will be a function of these adjustable parameters. Now in the next step, make use of the Rayleigh-Ritz formula to calculate the energy given by E0. Precisely I have written it for ground state. E0 of alpha 1, alpha 2, etc. alpha I, because this wave function psi itself is a function of alphas, equal to scalar product psi with this trial wave function h psi divided by scalar product psi with psi. If you are interested, once you have made a guess on this wave function, you can normalize the wave function using scalar product, using the mathematical idea scalar product psi by psi is equal to 1. Of course, that will give you the normalization constant. And once you are using this normalized wave function, you can eliminate the denominator as this is equal to 1. Now in the next step, we apply the variation to the above formula, Rayleigh-Ritz formula. Delta variation of this expectation value of energy with the trial wave function should be equal to 0. That means dou E0 by dou alpha I equal to 0. And equating this to 0 will definitely give you an equation in alphas. If there are n number of alphas, then there will be n number of equations. If you have n number of equations and n number of variables, you can easily solve them. You have so many methods, mathematical procedures of solving them. So this application of Rayleigh-Ritz formula will generate all the adjustable parameters that you have put forward or invoked while making the guess on the trial wave function. And suppose you have made a blind guess that, or what I must say funnily, uneducated guess, such that a parameter has no relevance, then that parameter will be obtained to have a value 0. It will be vanishing. So that is in fact the beauty of the mathematical procedure and a beauty of the variational method too. So once you have evaluated all these alpha i's, substitute these values of alpha I in the above equation for E, expectation value of energy that you have evaluated as a mathematical term in terms of the various alphas. That will give you an approximate value, or I have written it here in terms of the mathematical language, exact value of E0. If your method is so accurate, it will be exactly equal to the ground state energy, but seldom it might be. As variational method has this inherent drawback, there is a chance that your trial wave function, your gust wave function is different largely from the absolute wave function. If this difference is nominal, then you will be getting a more accurate evaluation of ground state energy or energy corresponding to that relevant quantum state. Now, once you have got this energy eigenvalue, in the last step, you substitute this alpha I in your trial wave function, and you can treat this as the wave function representing the system as well, because you do not have an absolute knowledge about the wave function. So more or less, this will be the nature of the wave function as represented by this trial wave function. So this is the procedure. So I have written it here 5 different steps. Actually, there are only 2 steps. First one, that is the most important step. Make an educated guess on the trial wave function. While making this guess, you will have to take into consideration behavior of the wave function at infinity, number of nodes present in the wave function or possible for the wave function, smoothness of the wave function, symmetry of the wave function, etc. And corresponding to each and every parameters that are not sure about, you will have to introduce adjustable parameters that forms the vital portion of the guess of the wave function. Once you have this wave function, you evaluate expectation value of expectation value of Hamiltonian using the Rayleigh-Ritz formula. Now in the third step, apply variation for it. That will give you a solution for all these alphas. And once you have got alpha, substitute this value of alpha in the expression for energy. Energy will be then solved exactly in the mathematical language. And substitute these values of alpha in the wave function. That will give you the most suitable wave function representing the system as well. Now, the applicability of the variational method to the excited states. If it is applicable for ground state, why don't it is applicable for excited state? It is applicable for excited states as well. But in the excited states, you have limitations. Even in the ground state, we have limitations because we have to take into consideration a lot of entities, and absolutely we will not be able to identify all those parameters that will have some relevance in the dynamics of the system, in the probability for finding the system even. If you cannot do it absolutely for ground state, how can we do it for the excited state as well? So the applicability will be limited as long as the excited states are concerned. And of course, once you have a very good knowledge about the behavior of the wave function in the excited state, you can make a more genuine guess for the excited state. And using that wave function, following the same procedure that we have made, evaluation of the expectation value of Hamiltonian for that particular quantum state with the relevant trial wave function that we have guessed, evaluate say energy, then apply variation, evaluate the values of the adjustable parameters, substitute them in the expression for energy and wave function. That will give you a calculation of the energy as well as wave function. And for the excited state, there is one more flexibility or one more limitation that could be used as a plus point as long as the assumption of the wave function is concerned. This is a quality of the eigenvectors of a Hermitian operator belonging to different eigenvalues. These are orthogonal. We are basically evaluating the energy eigenvalue, which are the eigenvalues of the Hermitian operator Hamiltonian. And the eigenvectors of Hamiltonian belonging to different eigenstates are orthogonal, are needed to be orthogonal. You have already made a guess for the wave function representing the ground state. Then definitely the guess that you have made for the first excited state will be a wave function that is orthogonal to the ground state wave function, whose exact nature has somewhat you have resolved by applying the variational principle. And for the next excited state, the wave function will be orthogonal to both the first wave function representing the ground state and the excited state. So that is true in the case of any particular trial wave function being guessed as scalar product psi I psi j equal to 0. Now with the help of this guess, we make a choice of psi and With the help of that choice of psi, we evaluate the energy eigenvalue and wave function following the procedure that we have already seen. Now we'll see